All right. So today's agenda, you have an assignment that was the uniform circular motion intro worksheet. We're going to take a quick look at that, let you kind of check some of your answers, get any questions you haven't asked and answered, and then I'll collect it and grade that. Then we're going to continue on with some notes on uniform circular motion. Not really a lot of notes. It's more like wrapping up what we did the other day, but making sure we get force sort of nailed down in your notes. It's pretty short in terms of the number of notes and the quantity of information, but a lot of scenarios we're going to talk through and kind of brainstorm to help you imagine the kinds of questions College Board might ask you. And then we're going to do our TOA GAMERB pre-lab discussion. So we're going to try to figure out how we could gain a mathematical and graphical relationship between multiple things today. So we'll brainstorm that. That's the lab we'll be putting you into your groups on Monday and having you start to think through what your procedure would be. And then on Wednesday next week, actually carrying out that experiment. And then we'll wrap it up by having you starting to work on the assignment, which is worksheet 1. So if you're watching the video, or Jackie, for you, you can find this on unit 3. It's just uniform circular motion worksheet number 1. And so you'll be able to find it on Axis in topics for unit 3. So keep that in mind as your assignment. Now worksheet 1, I'm going to ask you to get at least the first page done for Monday, but it's a short period Monday, so we'll only go through that part, and then I'm going to break into your groups and have you make sure you're ready for the lab on Wednesday. And then Wednesday, you'll need the whole period to get the data. It's a very lab intensive data collection process, so you'll need that whole time. And then next Friday, we'll be finishing up going over worksheet 1. We'll be looking at more problems through worksheet 3. I have a whole bunch of worksheets, so I just kind of pick different ones each year to give you a wide variety. It's impossible to go through everything that I have in my catalog, so I just kind of pick a random assortment so you get a good breadth of options to think through and really wrap it up. That'll be kind of the end of the unit next Friday. And so the following Monday, not this coming Monday, but the following Monday, then that would be our review day for this unit. And then that Wednesday after, so like a week and a half from now, that would be about when we're planning to take the test for this unit. So just so you can kind of plan ahead and be thinking, it's a little ways down the road, but want you to be aware of that. So any questions about time frame, what's coming ahead, due dates, anything like that? All right, so let's jump into that uniform circular motion intro worksheet. I'll just open up the key here on the screen. And I'm showing you these answers for 2 reasons. One, I want you to get a chance to check your work and make sure you're on the right track. And if you have problems, that we can get those questions corrected. But I also want us to think through the practical application. Are these scenarios you're reading about even realistic, first of all? And if they are realistic, why do some of the numbers end up being pretty small and some of the numbers end up being pretty large? Trying to figure that out. All right, so if we think about this first scenario, it says we got a 5 kilogram object. So what's like roughly 5 kilograms, just so we can get an idea about, is that heavy, is it light? Because not everyone's that familiar with kilograms.
It's like 11 pounds.
Yeah, it's like 10, 11 pounds, like a kind of a smallish bowling ball, but a bowling ball, not a ping pong ball or something. It's got some mass, but it's on the smaller side, right? So that's the mass that we're talking about. And it's spinning around a circle of a radius of 1 meter. So what's like a meter relative to? You know how long a meter stick is, right? So like a meter stick, that's the length of the radius, a little over a yard or a little over 3 feet. And its period is 4 seconds. So it's got basically a 2-yard or 6-foot diameter circle roughly. And it's going around that 6 meter diameter circle 1 time in 4 seconds. So 1001, 1002, 1003, 1004. So is it moving fast or slow? It starts here, 1001, 1002, 1003, 1004. Is that moving fast or slow? Pretty slow, right? So it's heavy. It's got a pretty big radius, roughly 6 feet in diameter, 3 feet in radius, and going pretty slow. So as we think about that, we can try to make sense of these numbers. So If it's taking 4 seconds just to make one cycle, how many cycles is it making per second? A quarter, 1/4. So in the first one, we just take the reciprocal of the 4 and you get 0.25 hertz. And hertz, the abbreviation Hz, just literally means per seconds. So you could also just have seconds to the -1. And then the velocity, if we use, I showed both ways here, you don't have to do both ways, but if you took the period that was given, you get 1.6 meters per second. If you took the frequency, which you determined for part A, you still get 1.6 meters per second. Just kind of showing you that both ways work. And that's, reasonably slow. It's not snail slow, but it's not car driving down the freeway slow, right, or fast. It's reasonably slow, which seems right since seems like it was moving slow when we thought about what the period meant. All right. And then what's the acceleration? Well, we have an equation for that. We can plug in the velocity that we just determined in part B. We can plug in the radius that was given in the beginning of the question, and its acceleration is 2.5 meters per second squared, less than the acceleration due to gravity, right? About a quarter of the acceleration due to gravity. So not super strong because it's moving so slow. And how did we use the mass in this problem? Griffin?
No.
We didn't.
Yeah, we didn't. So it's just a distractor. It's just there. I mean, you could use it for context to think about if I was actually doing this, how much force would be in the string or the cable or whatever, the rope. I could multiply that mass times c, the answer for c, the acceleration, and that would give me an insight into how strong the rope would have to be. But it doesn't really directly apply to anything the question's asking, right? But hopefully you can predict, like College Board might ask about what's the tension in the string, and then you would need the mass for that. But you just don't need it for what they've asked here. So any questions on number 1? All right, if we think about the context of number 2, 15 kilogram mass. So what are we talking about now?
93 pounds.
Yeah, that's like a small child or something. That's big, right? It's much bigger than before, 3 times the mass of before, 3 bowling balls, however you want to think about it. And now we got a radius of 5 meters. What are we talking about there? Yeah, 15, 16 feet, right? It's a pretty big radius. So diameter, like over 30 feet diameter. That's a big circle, and it's a big object. And its frequency is 25 hertz. What does that translate to? 25 hertz means
20 seconds, 20 circles per second.
25 times around the circle in 1 second. And this is a 30+ foot diameter circle. So that is moving, right? That's very fast to be going around that big of a circle 25 times every second. And so if we stop and think about what these numbers mean, the mass is sort of irrelevant, but it could help us imagine, oh, this would require a lot of force. We better have a pretty strong rope here if it's going to be able to take this small child and whip it around this circle at 25 times a second. Hopefully we wouldn't do that to a child, but maybe we better stick with the 3 bowling balls. We don't want to get arrested here. So, but that's going to be a crazy scenario. You'd have to have a really strong rope. So the mass can kind of just help us think about it that way. But the question of the period, it's just the reciprocal of the frequency. If it's 25 hertz, that means it's going around 1 time on this big 30+ foot diameter circle in 4/100ths of a second. All right, that's faster than we can blink. That's really fast. And then the velocity makes sense that it's so big now, because I had a few students say, am I supposed to be getting really big numbers on these? Because it seems so weird after doing number 1. Number 1 seems typical. Number 2 seems crazy, 790 meters per second. But if you stop and think about how fast that's moving, that makes sense. Yeah.
Why is there an asterisk velocity?
It's just based on the curriculum. It's like a code for teachers to know which ones are used in certain parts of the curriculum.
Oh.
Yeah, it doesn't have any special function for the students. And then for part C, you get an even crazier number because now you got to square that velocity. And so we end up getting 120,000 meters per second squared. That's way bigger than gravity, right? So just to kind of put things in context, I want you to be able to imagine what do these numbers really mean, especially period and hertz. I think a lot of times they can really help you start to imagine, is this even possible? And this one's, humanly speaking, that would be impossible. There's no way a person could do this, right? I think it would be pretty difficult for any kind of machine to even do this, because that is really moving. And the force required would be 120,000 meters per second times the 15 kilograms. So the force required would be massive, right? So I want you to be able to think through the questions and start to imagine what's going on and picture, is this scenario even realistic? And do the numbers make sense is maybe even more important. Why would I get this massive number? Oh, because it's really moving quick and it's got a big radius. All right, any questions about the first? We won't go through the backside necessarily unless you have questions, but I wanted you to be able to kind of check your answers on some of them and get you thinking through the application and kind of the practical, what's going on here, questions. So any questions from you guys? Jackie, you can always just unmute and chime in if you have any questions. All right, so if you're finished, just go ahead and turn it over here on the side stool here that is due today, and I'll check those over this weekend. Make sure your name's on it. And for those watching the video, if you're going to be back early next week, you can just bring it when you come back to school. Same for Jackie on Zoom. You can do that if you're going to be back early next week, or if not, if you're going to be out a lot of next week, then maybe just scan it and email it to me. All right, so that's good for the worksheet. And back to the agenda. All right, so now let's go ahead and continue on with our notes. And like I said, we really covered most everything last time, but we barely talked about force. It kind of came up tangentially, pun intended. We're gonna have a lot of nice puns today, so if you're paying attention, you can think of how bad of a dad joke it must be. So the idea here, though, is that we're gonna make sure we didn't miss anything when we were going through that, and it's gonna be focused on the dynamics. So when you see kinematics, that's focused on measuring motion, calculating motion. When you see dynamics, it's about forces, how the forces dynamically change the motion of the object. Instead of it being static, it's dynamic. It's not sitting still, it's not balanced forces, it's something's accelerating. There's a force that's causing some changes. And so when you see dynamics, think forces. So this first slide is really the heart and soul of today's lesson. This one slide pretty much has the guts of what you need to get. It says, for an object to be in uniform circular motion, there must be a net force acting on it. We already know the acceleration, so we can write the force. And we saw this equation in the NASA video, that because we know net force is just mass times acceleration based on Newton's second law, we can think about centripetal force, or in this case, they're using R. College Board uses C, just so you're aware. They're using R for radial. College Board and I typically use C for centripetal. So you can kind of substitute the word radial or centripetal. And on different websites, different worksheets, you might see it used either way. So here they're using R for radial. If I were writing it, I'd do C for centripetal. So centripetal force is mass times acceleration, but since we're talking specifically about centripetal force, we need centripetal acceleration. And we learned about centripetal acceleration in the last lesson, that we can calculate it by taking the velocity squared divided by the radius of its circular path. And so if I just multiply m times v squared over r, that would tell me the centripetal force. So it's not a very hard equation to derive, knowing Newton's second law and now knowing how to calculate centripetal acceleration. But it's an important one, and it's not one that's on College Board's formula sheet. So I don't think you would have trouble coming up with it on your own. The acceleration one is a equals v squared over r, but the force version is not. So just making sure you're aware of that. And in the picture, you can see that what we're going to recognize in the next couple slides, the force is directed to the center of the circle, and the velocity is tangent to the circle. So what's true about those two vectors, the force and velocity vectors?
Perpendicular.
They must be perpendicular. And so since the force is always directed to the center, it's going to keep changing its direction constantly. And since the velocity is always tangent to the circle, it's changing its direction constantly, but together they'll always make a right angle at any given point. All right. Now we're going to kind of think through a scenario to make sure we're understanding all the underlying nuances here. It says we can see that the force must be inward by thinking about a ball on a string, or like you'll be doing in lab, and we'll talk about that later this period, the stopper on a string. So if this was a ball instead of a stopper, same kind of an idea. We're just swinging it in a circle. And so in order for it to swing in a circle, there must be a force pulling it back to the middle, and we can see it would be the force of the string pulling on the ball. So the force of the string, or the tension in the string pulling the ball in, would be the centripetal force for this scenario. What's the centripetal force that holds the moon in orbit? Gravity. What was the centripetal force in the scenario on the one video with the guy using the little tennis ball and the hula hoop?
Friction.
Friction would make it slow down, but there's another thing that made it push to the middle.
Normal force.
The normal force, that contact of the hula hoop pushing. So often centripetal force is something pulling, like a string or gravity, but it can be something pushing, like that hula hoop, or if you're on a roller coaster going through a loop, right? The loop's rails, the track is pushing you back to the middle. So it can be a push or a pull, because forces are pushes or pulls. In this case, it's a pull by the string. Now there's other forces we could talk about. The hand is pulling on the string, and the string is pulling on the hand. The ball is pulling on the string, and the string is pulling on the ball. So we could describe the forces involved here, but the specific force making the ball go in a circle is the string pulling on the ball, and that we would call tension. So imagine the direction that a ball swinging in a circle on a string is actually moving at any one point in time. We know it's tangent, so we can see it drawn a couple places here on this circle. If you were to cut the string, the ball would keep moving straight out of the circular path. The direction of the velocity, as we said before, is always perpendicular to the radius of the circle. In this case, that radius of the circle will be represented by the string. And it is said to be tangent to the circle. So not much new here, just kind of a quick reminder of some of the things we covered last time. But making sure you're aware that the object would start off tangent to the circle. So I know it'd be hard to see from the back of the room fully, but if I have this stopper on the table and I'm just spinning it around, what are the forces on this stopper right now? There's going to be friction, there's tension in the string, normal force of the table lifting it up, gravity pulling it down, right? So what's going to be true about the gravity and normal force? They're equal and opposite, they cancel, they're balanced, right? Because the stopper's not rising or falling. And I'm sorry, Jackie, I imagine you can't see this because it's kind of right below the camera, but I'm just swirling this stopper around on the table. And then friction's going to make it slow down, which is why I have to keep putting energy in it to make it keep moving. Otherwise, if I just started it, if I quit putting energy into it, it just comes to rest because of the friction, right? But the reason it keeps turning on that circular path is because of the tension in the string. That's what's pulling it. Now, right now, the tension in the string is kind of at an angle, right? So which component is pulling it into the circle?
The X.
The X component. The Y component is just kind of reducing the normal force, right? It's just making it not push down against the table and table push up against it so much. Gravity's fixed because of the earth, but, and like, I can actually feel it as I go faster and faster. Sometimes I can actually feel it kind of, the friction reduces a bit because the normal force is weakened since I've got a Y component in the string. Okay, so lots of things to think about. Now, what if instead of a scenario like that, and hopefully you can see this on the video a little bit better, Jackie, and for those watching later, what if I do a vertical circle like this? So now, what are the forces here? Gravity, tension, It's really it. I mean, we can maybe say air resistance, but College Board says, normally we can ignore that. It's usually pretty negligible. So really just gravity and tension, right? But how is this different than that on the table with gravity and tension here? Yeah, Griffin?
The gravity's acting on it, like, and accelerating it more, I guess.
So sometimes the tension is going in the opposite direction of the gravity. Sometimes the tension is going in the same direction as gravity, right? So if you think about it at the bottom, like right there at the bottom of the circle, as it's swinging down, right there at the bottom, which direction is the gravitational force? Down. Which direction is tension? If it's at the bottom of the circle? Up. So we got gravity down and tension up. And so are they equal?
Yeah.
If they're equal, would the object keep going in a circle? Let me ask it another way.
No.
If they're equal, what's the net force?
0.
So what's the acceleration?
0.
But that's moving in a circle, so it has to have an acceleration, right? So the net force can't be 0. So which is greater there at the bottom of the circle? Is the tension greater or the gravity? Tension. Because it's pulling it back up, right? And so we could take the tension minus the gravity and find the net force. And then from that, we could find the net acceleration. Not the centripetal acceleration, but the net acceleration. There are two different kinds of acceleration, right? All right. What about at the top of the circle? If it's going around a vertical circle like this, what about at the top of the circle? What's true about gravity and tension?
Same direction.
Same direction. So what's the net force? How do I find the net force?
Add them.
Add them. At the bottom, I have to subtract them because they're opposite directions and the tension would be greater. At the top, I can add them and get the net force. So when you have something in a vertical circle, you got a few more things to think about. So like in a roller coaster, as you're riding on a roller coaster, you click, 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 and then you go down the hill, right? And as you're going down the hill, when you start to curve back up, how do you feel?
Feel heavier.
Yeah, you feel pushed into the seat, right? Because your body wants to keep going down, but the seat's curving you back to the middle, right? So what's the centripetal force? If you're being pushed back to the middle, what's pushing you back to the middle?
Normal force.
The normal force of the seat, right? It's pushing you back to the middle. Well, you keep going on the roller coaster and you come up the other side and then you go over a hill and you feel that in your stomach like, ooh, as you go over that hill, right? Well, what's making you curve there?
Gravity.
Gravity. Maybe a seatbelt too, depending on the ride, but gravity is what's pulling you back down there. So on a roller coaster ride, the centripetal force in different curves might be caused by different things, or even sometimes combinations of things. And so in vertical circles, whether it's a roller coaster or something spinning on a string vertically, like a yo-yo around the world, like the guy demonstrated in the video, there's a little bit more to think about. And we'll dig into some of those examples later next week. That'll be one of the big focuses of our lesson next Thursday, is really coming to terms with all the vertical things that's going on. But what I want you to start to understand is that they become a little more complicated because gravity is always down, but the centripetal is sometimes matching it and sometimes opposing it. And like on the side of the circle, if I'm thinking about this stopper going around the circle again, when it's on the side, like to my right, the tension is pulling it to the left, but gravity's straight down. So they're not opposing or assisting each other, right? So when there's a vertical circle, the net force overall is changing all the time because of the combination of how those things oppose each other or are perpendicular or assist each other. There's a lot more to think about with vertical circles. So in our lab, we're not gonna work with vertical circles. We're gonna do this horizontal circle, right? To try to minimize our need to think about the changing. Right now, gravity is gonna be affecting it consistently at all times in the same way, right? It's nearly perpendicular to the tension force, right? And it stays nearly perpendicular to the tension force, right? So that's how we're gonna simplify by doing a horizontal circle in our lab. But we will solve vertical ones and other problems and other examples later. Okay, moving on. So remember, the string is actually pulling toward the center of the circle no matter what point you look at it, top, bottom, right, left, whether it's vertical, whether it's horizontal. It is always true that if it's an object swinging in a circle, that string is always pulling it to the center. And remember, if it is a string or a rope, it has to be a pulling force because the ropes and strings can't push. Other things can, like the normal force of the roller coaster rails, but if it's a rope or a string, it can only pull. The string is applying a force toward the center seeking, centripetal, and therefore there must be an acceleration towards the center of the circle, the centripetal acceleration, the center seeking acceleration, right? So again, sort of just bringing this all around. And here we come to the final slide of this portion, bringing it full circle, unintended. This acceleration is called the centripetal or radial acceleration. This is almost like one of the first slides we did in our last lesson. It's just bringing it back around. The direction is always towards the center of the circle. That's why we call it centripetal, center seeking. And we learned last time we can calculate it by taking v squared divided by r. It's velocity tangent to the circle squared divided by the radius of the circular path. All right, any questions? All right, so now I want to cover a couple other scenarios to get you thinking about them. And I also want to talk to you about centrifugal force, because we've been talking about centripetal, P-E-T-A-L, but you've probably all heard the word or term centrifugal force, right? And so I want to make sure you understand the difference here and what we're talking about with that. I will say this, physicists will not really use the word centrifugal force, and I'll explain why here in a second. All right, so here we've got a couple scenarios here visually, then we'll read the words. So one, we've got, when the string breaks, the object takes off tangent to the circle. It doesn't have some sort of weird curving nature to it unless it's a vertical circle. Okay, so again, if I'm just spinning this around on the table, if the string breaks, it just goes straight, right? Unless it goes off the table. But if I'm swinging it in a vertical circle and the string breaks, it's going to start going tangent to the circle, but then what happens?
Gravity pulls that.
Gravity turns it into a projectile. So can you imagine the question College Board might ask? There's an object swinging in a circle. Part A, if the radius is this and whatever, find the acceleration, centripetal acceleration, or find the tangential velocity. Part B, if the string breaks when it's at some position, how far does it fly before it hits the ground? And so when the string breaks, it's going to start tangent to the circle. It might even give you the angle. And then let's say that it breaks when it's starting to come up this side. It's going to start like that, but then what path is it going to follow?
Projectile.
Which looks like
Parabola.
a parabola. It's going to go up and reach the peak and then come down, right? I've seen sometimes where they actually ask you to trace that path. One of them I've seen, and one that we'll practice, is a Tarzan question. So like Tarzan swinging on a vine. So, there's going to be a circular nature to it, right? Jumps off the branch, drops down, swings across the bottom, swings up the other side. But the vine breaks. So the vine breaks depending on where it breaks. If it breaks while Tarzan's coming down, he's going to go down fast, right? He's going to tangent to the circle. If it breaks while he's on the way back up the other side, he's going to start like this and become a parabola, right? Become a projectile following that parabolic path. And so all kinds of questions like, if it breaks now, how high does Tarzan reach before he starts to fall? Or, how far does he go before he hits the ground? All kinds of things that they could ask. And so I just want you to start to imagine that. But I want you to also notice this picture. These sparks are all coming off tangent to the circle depending on where they're originating. If it originates right here, it's pretty much straight out. If it originates right here, it's coming more at this angle. If it's down on this tip, it's coming more at this angle. So depending on which part of the metal contact is generating the spark, it's coming off tangent to the circle. And you can see most of them are kind of right here because most of the contact is right at that spot. The third thing on this slide, so there's lots kind of embedded in this slide that we want to mention. It says, there is no centrifugal force pointing outward. So on this ball, there is no force making the ball do this. Right? There's no force making the ball do that. However, the natural tendency of the object to move in a straight line, which we call inertia, must be overcome to make it go in a circle. So the ball wants to go this way naturally because of its inertia and momentum. If the string breaks, it's not that there's a force making it go that way. It's that it already wanted to go that way because of its inertia and momentum. The force was the string not letting it do that. The force was the string pulling it back into the circle. When the string breaks, there's no force, it goes straight, according to Newton's first law. So centrifugal force isn't a force. So when people say centrifugal force, they're really just talking about the object's inertia, which isn't a force, it's a property of matter based on its mass. And so that's why you won't really hear physicists saying centrifugal force, because it's not a force, it's the inertia of the object. Another example, you probably felt this before. You're on a bus or in a car, you're not driving, so you're not really paying attention. The driver has to swerve for some reason, and you get slammed into the door, or slammed into the person beside you, or something like that, right? So you think, oh, there was a centrifugal force making me slam into the door. But that's not what happens at all. Try to picture what's happening kind of frame by frame. You're in the car. You're driving straight. So what way does your body want to go? Straight. The car turns, you fly into the door. The door didn't hit you, right? Your body's inertia carried you into the door, or carried you into the person the car turned out from underneath you. And if there wasn't enough friction, you might slide across the seat, or you might just lean over because you're losing that force pulling you in a circle. And like the top part of your body, there's nothing touching you, right? So you kind of tip over because there's nothing holding the top part of you into the circle. Your body wants to go straight. Another one, my daughters, and now my granddaughter, loves merry-go-rounds. Every time I go to the park now, she lives they moved to Texas, but when she was here, always, Grandpa, put me on the merry-go-round. And she's faster, faster, faster. And I'm always cautious with my granddaughter because I had a bad experience with my actual daughter when she was about 3. We were having a good time at the park. She's on the merry-go-round. She said, faster, Daddy, faster. And I'm pushing the thing hard, and she's flying around in a circle. And she got so excited, she started to clap and let go. And so while she was hanging on, there was a force keeping her in a circle. As soon as she let go, centripetal force was gone, and her inertia made her fly off the merry-go-round. And it was no longer, yay, Daddy, yay, Daddy. It was a lot of tears. And why did you do that? Because she was little, didn't understand. And I had to learn the lesson of, I need to tell little kids, like, hang on or you'll fly off, because they don't know physics. But that's not centrifugal force. It was her inertia. There was no force that made her fly off. Her body just wanted to go straight. And when she let go, there was no force to pull her into the circle, so she did go straight off into the grass.
Thank you.
So centrifugal force doesn't exist as a force. It's really just the inertia and the momentum of an object. And momentum we've mentioned before, and we're going to come back to it again. I think it's our next unit after this one. Momentum is actually like force. It's mass times velocity. Force is mass times acceleration. Momentum is mass times velocity. So objects with velocity have momentum, and objects with mass have inertia. So an object's inertia and momentum are what carry it forward instead of centrifugal force. So if you, have any of you ever used a centrifuge? Like in biology or chemistry or anything? Not yet? A centrifuge is a device, you put test tubes in it, and they're usually kind of at an angle, and then it spins it really fast. So in a hospital, they use it and they put blood in there, and then all the blood cells and platelets end up at the bottom of the tube, and all the plasma ends up at the top. Or I used it in chemistry. A lot of you had chemistry, you know what a precipitate is. Take two aqueous solutions and mix them, and it forms a solid product. And so we would often want to separate the solid precipitate out to see what its mass was, doing stoichiometry, trying to prove the math. And so we would put it in here. The precipitate would end up at the bottom of the test tube, and the liquid would end up at the top that we could decant off later and then find the mass of the solid. So it's called a centrifuge because they're thinking it's centrifugal force that pushes those particles to the bottom of the tube. But there is no such thing as centrifugal force. It's just the inertia of the particles. So if a particle has more mass, it has more inertia, right? All the particles want to go straight, but the bigger particles want to go straight more because they have more inertia. And so the bigger particles, they're trying to go straight, but the test tube's pushing them back. And because they have more inertia, they end up reaching the bottom of the test tube faster. As they're trying to go straight, the test tube slams them back, and they try to go straight, the test tube slams them back. And the test tube is actually pushing them to the center. And it's really kind of creating an almost artificial gravity where the denser things end up on the outside. Gravity in this case is the outside direction. Gravity normally is the mass drawing us to the center, right? Artificial gravity is that we feel it outward because of the normal force pushing in. So when they were talking in that NASA video of making a space station rotate to create artificial gravity, it's not because there's any mass, it's because it's spinning, so your body's trying to go that way and it's pushing you back into the circle. And so you feel pushed against the ground as it keeps pushing you back to the circle. And so that's why it's not real gravity, it's artificial. But because of that centripetal normal force pushing you constantly back to the center, you feel like you're being pushed into the ground, when actually it's just your inertia trying to go straight and the ground pushing you back to the center. So a centrifuge would be better named a centripete. It is really centripetal, not centrifugal force, right? Or an inertia machine or something. So centrifuge is kind of a misnomer because centrifugal force doesn't exist as a force. It's a misnomer. All right. Any questions about the lesson today? About the falsehood of centrifugal force? About centripetal force? All right. So wrap it up with a few questions here. When an object experiences uniform circular motion, the direction of the net force is A, in the same direction as the motion of the object, B, in the opposite direction of the motion of the object, C, directed toward the center of the circular path, or D, directed away from the center of the circular path. Which one is it? C. If it's uniform circular motion, that net force is the centripetal force pushing it back to the center. All right. Next question. A boy whirls a toy at the end of a string around his head. The string makes one complete revolution every second. What does that little phrase there, one complete revolution every second, translate to in terms of our variables? Frequency. It's basically saying one cycle per second, so 1 hertz. Okay. He keeps the radius constant, but decreases the speed so that the string makes 1 revolution every 2 seconds. So what just happened to the frequency? It's now half a cycle per second, right? It got cut in half. You could also think about it as the period if that's easier. What happens to the tension of the string? If the frequency got cut in half, or you could say if the period doubled, however you want to think about it, what would happen to the tension in the string?
D. Right?
D is delta, is that what you're saying?
I think so.
Okay,
I can do the math though.
still thinking it through. First guess, D. How about some of the rest of you? What do you think? You agree with D? Any ideas? Thank you. You're welcome. This is a proportional reasoning one, so let's look at the equations over here. Here's one of them. Velocity is circumference times frequency. Well, what just happened to the frequency? Half. What does that tell us about the velocity then? That's half. Okay, because they're directly proportional. So this gets cut in half, that gets cut in half. All right? But the question doesn't ask about the velocity, it asks about the tension. What's a tension? That's force. So if the velocity got cut in half, and we need to find the tension force, what is the velocity if it's cut in half and we square that? That's going to make the force 1/4. So it's going to cut it by 1/4. Okay, so D is the correct answer. All right, one more. These proportional reasoning questions are super common on the multiple choice part. All right, this is a multiple correct, so there are 2 correct answers of the ones below. An object is moving in uniform circular motion with a mass m, a speed v, and a radius r. Which of the following will quadruple the centripetal force on the object? 2 of them are correct. Ideas?
Is
Yeah,
it A
Brennan?
and C?
A and C. Got 1 vote for A and C. See a couple people nodding. Griffin?
I thought A and D.
A and D. So you agree with A, but think maybe D instead of C? I see a couple people nodding at that now. Let's talk about A first then. Let's see if that makes sense, because we got some agreement there. Does doubling the speed quadruple the force? So if we double this, well, that's going to be squared, so that would quadruple the force. So A, definitely for sure. Cutting the speed to 1/2. Well, in A, we just said doubling it would make it quadruple, so doing half instead wouldn't work, so we can cancel B out. No one mentioned that one either. Cutting the radius to 1/2. Okay, well, if we put half in the denominator, what does that do to the force?
Doubles it.
It would only double it, right? So, because dividing by half is the same as multiplying by 2. So dividing by half is multiplying this by 2. So to make it quadruple, we do need to do what D says. We need to make the radius by 1/4, because it's inverse but linear, right? Well, not, I guess not really linear, but inversely proportional. So it's not going to be quadratic. This is quadratic. Okay. Questions? All right. So we're gonna brainstorm a little bit about your lab. We've talked about what you'll be doing, but we're gonna kind of come up with some more details here. Can I get a volunteer to be our recorder here and help me put a few things on the screen? Just basically jotting down. We're gonna brainstorm what you observe as I demonstrate, and then we just need someone to write it down. Someone willing to do that? You got it. Thanks, Michelle. So when you do the experiment next week, you'll be getting with your partners, and you'll basically just be swinging the stopper around. And you might swing at this speed, you might swing it faster, you might swing it slower, you might use the same size stopper I have, you might use a different size stopper, you might use the same size weight, you might use a different size, but as I show you the process here, what are some things you notice? What are some things you observe as I illustrate what you'll be doing? Just anything you observe.
Faster speed, more force,
The faster the speed, and how do you know there's more force?
because it lifts the weight higher.
Yeah, so the faster I spin this, the more that raises, right? And you just jot it down in your own words, however you want to summarize.
Because there's more gravitational potential.
Now, we don't really want to explain it yet. I mean, it's good to think about that, but in terms of what we record here, we're just gonna say, like, what are we seeing? And then we can explain it later. And you can say the explanation now, but we're just gonna record what we see. So the faster the speed, this goes up, right? The weight goes up.
How'd you record that in a diagram? Because you can't exactly do the weight force because the weight force would remain the same.
Right, so I'm not sure, I guess I'm not sure I understand your question yet.
Okay, so if you're in a diagram, like the force downward is the weight force, and then the force, I guess, the tension force up and outward is equal to the centrifugal force, right? So how would you record that there's more force?
When I'm faster?
Yeah.
Yeah, so a free body diagram always shows at a point in time, a certain instant.
Okay.
And so you'd have to do multiples, like when it's this one, it looks like that, and when it's this one, it looks like that, so you could see it changing over time.
Okay.
Yeah, that's a good question. Free body diagrams only show one thing at a time, or one instant at a time. All right, so what other things do you know? So if I make it go faster, the weight rises, that's one thing.
It also seems like the radius increases
As
you spin fast.
Okay, so as I spin faster and the weight rises, the radius also increases, the radius of that circular path above. What else do you notice? Faster or slower, what happens there?
Constant speed that has balanced forces.
Okay, so if I keep it at a constant speed, it seems like the forces seem more balanced. And Michelle, you can click on that X and it'll take that off the screen for you. Constant speeds makes it seem like the forces are more balanced. Anything else? So you can see this is a constant speed and you can see the radius at this setting, right? And then if I make this the constant speed, what do we notice? What did I do to the constant speed? Constant speed went up, and what happened? What changed?
Radius increase.
Radius increased, right? So make note of that. If it was a constant speed, it was constant forces or balanced forces, but faster speed, make the radius increase, and slower speed.
Does that mean that you're keeping like the same like rotations per second?
Yeah, say keeping the same frequency or the same period of time.
Regardless of like speed, the rotations per second would be the same because as like speed increases, the radius also.
Mhm. Yeah. So that's like a conclusion we can draw from what we're seeing there. Good. Anything else you notice? I think we've kind of got it phrased a couple different ways there, a few different things we're seeing. Anything else that stuck out? Got it all? All right. So go ahead and go to the next slide there, Michelle. What are some things we can measure?
Period duration,
Sorry?
like how long it takes for one period.
Okay, so we can measure the time.
Yeah.
And we could use that as period or frequency, like we could figure it out either way, whichever way, so time. What else could we measure?
Weight.
Which we can measure the weight. Usually when something's hanging like this, I don't know if you guys have heard of the term plumb bob, or like on a pendulum, a bob is the part that swings, so we can call this the bob, so the weight of the bob.
Radius. And also circle.
Okay, we can measure the radius of the circle.
Couldn't that be in what we manipulate though, rather?
Could be. We're gonna figure out first what we can measure. And so we can measure radius of the circle. I think, did I cut somebody else off? Yeah, Griffin?
Velocity.
We could calculate the velocity, right? I don't think we have any instrument that would help us to measure it directly. See if I can do this without smacking myself on the head. I'm not left-handed, but I'll try. So we could determine the velocity, but not measure it directly. Anything else we can measure? Back to what we observe, you hear the noise? What's causing that? Friction. So just something to keep in mind, that would be a source of error, right? We're losing some energy somehow because there's some friction. There's one more thing we can measure.
Is it the weight on the end of the string?
Yeah, the weight of the stopper. Because the stopper, we have different sizes. So you could use this size, or I think we might have a little bit bigger ones and definitely have some smaller ones. So we could also measure the mass of the stopper. There we go. All right. Thanks, Michelle. I think those are the things we can measure after our observations. So now of those things that we can measure, what can we manipulate? Which ones would be easier to change?
Weight of bob and weight of stopper.
Yeah, that's pretty easy, right? I mean, let's actually use a different color here. We'll do, oops, go purple. So the weight of the bob, that would be pretty easy to change. We have all those weights back there. And I mentioned that we've got different kinds of stoppers, so that would be pretty easy to change.
The radius of the circle.
Yeah, that wouldn't be too hard because we could just like put some tape on the string below or something and then stop it spinning, and you know, as long as the tape is in that spot, we can measure the radius. That wouldn't be too hard to measure or to change. Because you saw, the faster I spun it, then the bigger the radius got, and the smaller, or the slower I spun it, the smaller, so we could kind of adjust that. So could we adjust the time it takes to go around? Kind of indirectly, right? It's not, it would be harder to say, hey, let's make it go around 1 second. Like one time in one, that'd be much harder to manipulate. It's not necessarily impossible, but much more difficult. So let's make this our dependent, because it'd be easier to see how that changes than to actually manipulate it, right? And then we've got 3 independents. 3 things that we can manipulate. Now, according to the fair test rule, how many of those things can we manipulate at once? One at a time. So we need to either change the weight of the stopper and keep the weight of the bob and the radius constant, or change the weight of the bob and keep the radius and the stopper constant. We can only do those one at a time. All right, and on Monday, when I get you in your groups, I'll put this back up on the screen and remind you of what we came up with. But we want to make sure we're using the weight of the bob, the radius of the circle, and the weight of the stopper as our independent. So we're kind of doing 3 mini experiments in one. We'll test this, get our data, test that, get our data, test that, get our data. And I want you to prioritize it this way. I want to make sure we test this one. Oh, sorry, that's not the priority. Where's my undo? Behind here, I think. There we go. We want to prioritize this one, weight of the bob, and we want to prioritize this one. And because we only have 1 day to collect the data, you should have enough time to do that. If you can do this one, that'd be great. If you have time, but save it for last. And what I'll make sure we do is either within this class or in my 4 different classes, I'll make sure that different groups are using different size stoppers so that we could collaborate and share data across groups to do that 3rd one if you don't have time to do it yourself. So some groups will probably have time to do the 3rd part, others won't. Make that your 3rd priority so that because we could always do that across groups if we need to. Okay? So any questions about what you'll be doing in the lab or what you're going to be trying to measure and manipulate and test in the experiment? All right, so we will be doing the setup Monday we'll start with worksheet 1, we'll go over part of worksheet 1 together, then we'll break, we'll put you into your small groups that are gonna be doing this experiment together. You'll brainstorm your procedures, start filling in your journal, putting it in the table of contents, writing your purpose statement, maybe even putting together your procedure, making sure you all agree on how you're gonna try to measure. Are you gonna use video? Are you gonna try to do stopwatch? As a group, you'll brainstorm what you're gonna do Monday. Because Tuesday, you need to come in with a plan. If Tuesday you come in and you're like, okay, now what are we gonna do? You won't get done probably with even 2 of the 3, let alone all 3. You have to have a plan. So that's Monday. About half the period you'll be with your group making a plan. How are we gonna do this? How are we gonna make those measurements? All right? And on Monday, I'll give you the rubric, which shows, all the little checklist of the things you're gonna need to include. And I did put down here in the required graphs, 2 of them. We're gonna kind of see how it goes. I made the dots a little different because the stopper mass graphs, if we have enough data and we can do that, great. If not, we can end up trimming that out of the requirement. So I've got it kind of highlighted specifically. And then I don't usually do this, but because there's so much going on, I'm also giving you not a table to actually use, but sort of a template to look at of all the things you will be measuring and manipulating, and also all the things you'll be calculating from those measurements. So rather than having you try to figure it all out, I'm trying to give you at least a little assist here to say, okay, make sure in your data tables you've got this kind of stuff included. You can organize it however you want, but this will at least give you a starting point as a template. All right, so I'll give those out Monday. You'll get your groups, you'll brainstorm your procedure, start setting up your journal, and then on Wednesday, you want to have that day just to purely collect data because it'll take some time. And we'll have some of you working in here, we'll have some of you working out there because we don't want you smacking each other in the head with the stopper and stuff. So try not to get anybody injured. All right, any questions about the experiment? All right, the assignment today, I'm just gonna have about the last 20 minutes here to just get started on the assignment. I do wanna make sure you get the whole first page done by Monday, and you'll probably get that done in class. And then you need to have the entire thing done by next Friday so we can wrap up what we don't have time for Monday. So if you didn't pick up the worksheet, it's on the back table. And you've got about 20 minutes to get a good start on it right now. And you're welcome to kind of help each other and discuss it as you go. It's not a quiz or anything, so don't mind if you collaborate at all.